multiscale models, and this is work with Andy and Boulem and Ying Han, who used to be Boulem's postdoc, and an undergrad, Dimitri Skiorshammer. And among the different aspects of convective momentum transport, these are kind of some of the main ones we'll be thinking about. Basically thinking about it in terms of energy transfers between scales. And we're going to see that this could be upscale transfer, meaning that energy is transferred to the larger scales are accelerated. Or it could be the other way. The larger scale could be damped by the convection. And we're also going to be thinking about this in the context of parameterizations and models. So resolved scale processes interacting with subgrid scale processes. So a couple of the themes will be multiscale modeling and stochastic subgrid scale parameterization. So there'll be four main kind of topics here, three about multiscale modeling to try to better understand some of these processes to inform how to best represent them in this last topic here. Okay. So just to set the stage, this is kind of the basic picture of convective momentum transport of an organized convective system. So this is momentum transport from a squall line. So this is just a cartoon of a squall line to show sort of the tilted updraft and also descending inflow as well. So when you have a tilted updraft like this, it gives you correlations between horizontal and vertical velocity, W prime, U prime. And then if you take minus the derivative of that, you get the actual acceleration that would happen over the horizontal average of the domain. And so this is the momentum transport in this case. So for an updraft tilted in this direction, you get acceleration of westerlies in the lower part of the troposphere. Okay, and so that's kind of the picture, or at least one aspect of the picture of mesoscale convection and convective momentum transport. And there's been a lot of work done trying to understand that type of thing. Another, I guess this will probably be more of the focus here in this talk than mesoscale, is going to be convective momentum transport due to actually synoptic scale convection, so convectively coupled waves. And there's been a decent amount of work on this topic as well. And I would say that this case is probably less understood than the mesoscale case. It'd be interesting to see some more observational work done in this area, and hopefully this talk will motivate some of that. Okay. So this is just a cartoon that kind of hints at why there should be momentum transport due to synoptic scale structures. So this is a cartoon of a convectively coupled Kelvin wave. And when these people draw these cartoons, they have a tilted updraft. So right away that tells you that there should be momentum transport due to actual synoptic scale circulations. And so I guess I should also point out, I'm going to be using the term convective momentum transport in a sort of broad sense here. This is not just convective momentum transport on scales of individual updrafts and downdrafts or on mesoscales. I'm using that for a synoptic scale updraft, downdraft circulation here. And so this is the exact same picture from that earlier slide. And so this type of acceleration, accelerating westerlies at low levels, there's been some theory by Maida and Bielo that suggests that this could be responsible for accelerating westerly wind bursts or accelerating it aloft or contributing to its intensification. But at the same time, there's other types of synoptic scale convectively coupled waves. For instance, two-day waves or westward inertial gravity waves. And if you look at the cartoons of these, or the real data too, there's also a tilted updraft, but it tilts in the opposite direction. So now for this case, you get the opposite type of acceleration. So now we're accelerating easterlies in the lower troposphere. So it makes you wonder, in any given situation, what's going on? How does the mean wind interact with convectively coupled waves and their momentum transports and things? So as we just saw, The acceleration or deceleration depends on the sign of the CMT, and we just saw that that depends on the propagation direction of the wave. Is it an eastward propagating Kelvin wave tilted one way, or is it a two-day wave that's tilted the other way? But as we'll see here in a minute, the propagation direction of the convectively coupled wave actually depends on the mean wind, the shear. The shear, as we'll see in a little bit, can actually favor a Kelvin wave over a two-day wave. So this is a bit of a chicken-egg question, because now we're right back to where we started. So this also suggests that rather than trying to think about just the one-way problem, where you say, I have a background state, what do the waves do in it? Or the other one-way problem, I have a wave, how does it affect the background state? We should really be looking at two-way interactions between the two. And besides just the academic problem of understanding those two-way interactions, this is really kind of at the heart of things like the Madden-Julian oscillation. So you might ask the same question in the context of the MJO. How does the MJO envelope interact with those waves that are within the envelope? Is it a one-way interaction, or is there a sort of cooperative interaction between the two? And the work that I'm going to show here in a little bit is going to suggest that there's cooperative interactions between the two in different ways. In this talk, we're going to be focusing on interactions involving momentum. You might also expect that there should be interactions between the two involving moisture and temperature and things like that. But I won't be talking about that at all in this talk. But I think Andy will in one of his talks. You know the MJO skeleton model? Well, just a little bit? Yeah. Okay, so this is work. This work is basically going to be a model for convectively coupled wave mean flow interaction. And this was published in JAZ in 2009. Okay, so this is the basics of the model, illustrated here using just the momentum equations. There's the full set of variables, momentum, temperature, and all that. But I'm just going to illustrate it with the momentum variable. So we have a mean flow, U bar, it's a function of height and time, and it's a function of a big T, whereas there's going to be a wave, little u prime, that depends on a smaller time scale. And so the mean wind is driven by the momentum transport from the wave. The wave feel the mean wind through these advection terms, vector advection terms. And so I guess I should also mention, yeah, so this big T up here is a longer time scale. We have a multiscale asymptotic derivation of this model, but I'm not going to go through any of the details of that. Let's see. So a couple of other key points are that if this is going to be active, we need a model that has tilts, waves with tilts in them. So, excuse me? What is this term here? This S? Yeah, that's another key point. So there's a couple of things that are kind of not yet determined on this slide. So one is, how are we going to get waves with tilts? And the other thing is, what is this S in these source terms? And so, yeah. Yeah. Yeah, I wrote et cetera. There's more variables too. The W equation? So this is going to be a hydrostatic model, so there won't be a thing. Oh, the W prime, well, it's going to be a shallow water. It's going to, how about if I just describe it? Maybe that's a good answer. So to make sure that we have tilts and to actually determine what those source terms are on the right-hand side, we're going to use the multi-cloud model of Kuder and Maida. So I won't have to describe this much because you just heard all about it. But you know, it has two vertical modes, which allows you to have tilts. It has parameterizations of different cloud types. In addition to what Buelam showed, we're going to add well, I guess he had nonlinear advection in the GCM version, but we're going to add nonlinear advection to the model in a third baroclinic mode too. So that will then specify the source terms. Those come from the multi-cloud model. So the U prime equations are basically the multi-cloud model with advection terms added, and then this term is self-explanatory. Okay, and this is the type of behavior that the model shows now that it can interact with a mean wind. So what we see is that there's convectively coupled wave mean flow interactions, and we get an oscillation that's on intraseasonal timescales. So this is 50 days here. It's a 6,000 kilometer periodic domain. There's a westward propagating wave that's propagating around for a while. It dies, and then an eastward propagating wave forms. And this kind of cycle of eastward propagating wave forming, dying, westward propagating wave forming, dying, that just repeats. So that's the intraseasonal type of oscillation. It's not necessarily an oscillation that happens in nature, but that's the time scale of it. And so at the same time that these waves are forming and dying, the mean wind, for instance, so we start off down here in let's see, it's the thin solid line, so it's the one with a low-level jet. So when there's this low-level jet, it is the westward propagating wave that seems to be favored, but that wave has momentum transports, and those momentum transports are going to damp this jet and give us a more or less linear profile. And that forms by time 1025, so about right here. So now in this new shear, this westward propagating wave is not the favored wave. It's the eastward propagating wave. So it dies, and eventually the eastward propagating wave forms and keeps going. And before I move on to the next slide to show what's next, I should make sure I mentioned all these things here. So, so I just described how this interaction works between the shear and the wave propagation direction. I should also point out right now that it's kind of interesting that we get, sometimes it's more or less a coherent synoptic scale feature, but at other times it's an actual wave envelope on the synoptic scales with squall line-like features within it. And this is going to come up later in the talk. And I should also just mention that here the mean wind was damped, so this is downscale energy transfer. Okay, but if we continue, just starting right from the top here, and go for another 50 days, this eastward propagating wave, that's going to accelerate this jet, this westerly jet in the lower troposphere. And this is kind of like what happens with the westerly wind burst phase of the MJO in the presence of a Kelvin wave. But then in this new shear, it's the westward propagating wave that's favored, so the Kelvin wave dies and the westward propagating wave forms. And this just repeats. Say it again, the westward propagating wave? Well, it would be a westward inertial gravity wave. Yeah, right. This model is actually just above the equator, so there's not actually these beta plane waves. It's just a convectively coupled gravity wave. But yeah, and so I guess the other, yeah, we'll get. So the other thing I should point out here is now in this case, this jet was accelerated. So now we're seeing upscale energy transfer in this case. So what we've just seen here in this little example is that convectively coupled wave momentum transport, it can have upscale energy transfer or downscale. It kind of depends on the situation. And this slide is just illustrating what was going on. I mentioned this mechanism that one wave is favored over the other one. So this is showing linear stability theory for two cases, either with no background wind or with a background wind. So if there's no background wind, there's east-west symmetry. There's eastward unstable modes and westward unstable modes, and their growth rates lie on top of each other. As soon as we introduce a background wind, and I'm using the jet shear background wind for this right column, now there's an asymmetry between the eastward and westward propagating waves. It's the, oh, did I pick a different wind? Which one is it? The westward propagating wave. Yeah, the westward propagating wave is favored in this case. Yeah, on large scales. And it's also interesting that at smaller scales, there are eastward propagating waves with a positive growth rate. So these are those squall line-like features that appeared in that slide. Okay, so I guess the main point of this piece here is that in in the situation of momentum transport with convectively coupled waves, and I guess for mesoscale systems too, there could be upscale or downscale kinetic energy transfers. One thing that you might start wondering about here is, we've talked about mesoscale and synoptic scale momentum transports. You might start to wonder, in these situations where you have a multiscale wave, what are the relative roles of these two? So if we go back to this picture and think about what happens when you have a multiscale wave. So, like right here, there's an envelope. There's a synoptic scale envelope and mesoscale squall lines here. They should both be transporting momentum in some ways. So you might wonder, what is the relative role of the synoptic scale guy versus the mesoscale one? And this is a common feature in nature. So these are plots from Nakazawa from observations and from Grabowski and Moncrief in a cloud resolving model, where this is a very common feature where you have some envelope with smaller scale fluctuations within it. Okay, so now we're going to try to understand this question in the context of the multi-cloud model. Okay, and this is in a paper in JAZ from, I guess this is last year now. Okay, and so this is looking at the case that we've just been talking about. But if we had a beta plane model instead of just above the equator. So what we're going to look at is the linear instabilities that arise in this background shear. And we're going to use this jet shear right here on this slide, but we consider the other shear cases in the paper. So what we're going to do is we're going to look at this this plot. So as Bullen was showing, it's these dark circles that are the unstable ones, and they have a growth rate proportional to the size of the circle. So in this case, it's the wig waves that have the strongest growth rates of about 0.7 per day. And then there's this new type of mode that appears. This slope here corresponds to waves that propagate at about 8 meters per second. And if you look at the structure of these waves too, you would be convinced that these are kind of like squall lines. So these are those squall line-like features within the envelope of the wig wave. Okay, and then we wanted to ask this question about what would be the relative role of the two in terms of their momentum transports. So one simple way that you might suppose that you could identify their momentum transport is that suppose their momentum transport impact is proportional to how strong their growth rate is, as a first supposition for how to do this. But there's some caveats with that we'll get to in a little bit. So in this case, you would say that it's the momentum transport due to the wig wave that is the most important, and that was the case in those simulations. Okay, and we could try to do a similar kind of thing for different background states. So now, another thing we looked at in that paper was, what if we took a sequence of MJO background states and looked at the different instabilities that arise? So we're going to take a sort of theoretical-looking zonal wind profile, a sequence of states through here, and we're going to also look at changing moisture background state at the same time. The things that distinguish the different moisture background states are, for instance, how strong, how moist is the lower troposphere compared to the upper troposphere in different situations. So in the onset phase, we would have a moist low level transitioning to moist at upper levels in a later phase, type of natural transition. And this inset is supposed to be showing that the two flip their roles. Dashed is drier here, but moisture in the upper troposphere. Okay, so now with those background states, we can do the same kind of thing. We can look at the linear instabilities, and we see waves on different scales through the whole sequence. So at the earlier stage, sort of the convective onset of the MJO, it's the Kelvin waves that have the strongest growth, and those would tend to decelerate the winds at that time. At the mature convection stage, there are squall line-like features as well as unstable Kelvin waves. So those two would have kind of competing momentum transport effects. And in this later stage, around the westerly wind burst time in the convective decline, it's these squall lines that have the largest growth rates. And those would tend to, if they're eastward propagating, they would tend to accelerate that westerly wind version. And we considered other cases in between these that are in the paper too. So what we just went through was a sequence of kind of frozen background states to try to understand plausible CMT feedbacks and the competition between which one is more important, the synoptic scale feature or the mesoscale feature. One caveat for this interpretation, so we used a simple supposition there. We said, let's suppose that the CMT impact of the wave is proportional to its linear growth rate. There's plenty of reasons why that might not be the best thing to assume. One reason is that a strong growth rate should imply strong growth, not necessarily that the amplitude of the wave right then is the largest. So another way of saying this is that there's actually a time delay in the convective response to the background state, right? If the growth rate is strong, it just means that the wave its amplitude is growing. So to try to understand this time delay more, you kind of need to think about a temporally varying model and two-way interactions. And so you could see that time delay a little bit in some of this earlier simulation. So the shear had become this linear profile by about right here, which was unfavorable for the wig wave. But it took that wig wave 10 or 15 days before it finally had zero amplitude. Or another way of looking is that the growth of this Kelvin wave, that Kelvin wave was the preferred wave at this time. But you see here that it is not the wave that is present at this time. It took 10 or 15 days before the Kelvin wave actually became present. Okay, so to try to understand these time delays now, and these are going to be an important piece later, we're going to just illustrate this with some simple amplitude equation models. And this is in a paper that should appear soon in Theoretical and Computational Fluid Dynamics. So this is a simple model to try to illustrate this time delay and the delayed response. So we're just going to have ODEs for three variables, a mean shear variable, big U, an amplitude of eastward moving waves, like convectively coupled Kelvin waves, and an amplitude of the westward moving convectively coupled waves. And so this is a simple model that has the features of what was going on earlier. So the mean shear it feels momentum transport from the waves in different ways, as we saw before. The eastward and westward propagating waves have opposite momentum transport effects, so that's why one has a positive sign and the other a negative. And the effect of the mean wind on the waves comes through this type of term here. So a positive U is going to cause the eastward propagating wave to decay, whereas it's going to cause the westward propagating wave to grow. So this is sort of that time delay, that response built into a model in a simple way. So the mean wind has an effect on the growth and decay of the waves. It doesn't immediately tell you what's there or what's not. And so if you run this model, you end up with oscillations that look a heck of a lot like the simulations from before. So you'll have one wave appear, and then its momentum transport causes the sign of the shear to change. It decays, the other wave forms, and it keeps repeating. And so you might be wondering, where did we come up with this model? So there's more motivation for it than just kind of coming up with a simple type of way. You can derive models like this using systematic asymptotics, and this is carried out in other contexts. We did not actually carry out this type of asymptotics for this model because it has all sorts of nonlinear switches and things that would make it hard. But the way it works in these other contexts is that you have a wave ansatz for your eastward and westward propagating waves. So there is a wave amplitude that varies on a long time scale. This bold E is the eigenvector for it, and then it's a sinusoidal fluctuations with its frequency omega plus, and similarly for the other wave. And so if you plug this into your governing equations and ask how should these amplitudes evolve in time, in all sorts of different contexts you get equations kind of like this. They're kind of complex Ginsburg-Landau type equations. So there's growth decay terms, and then there's nonlinear damping-like terms, well, I guess depending on the sign of beta, and also nonlinear interaction terms for the waves interacting with each other. So that previous model from this slide, these types of terms are the linear terms that would tend to come from right here if you ignored the nonlinear interactions there. But you could also take this type of model. So now if we look at amplitude equations with some more complexity, so now if we actually include some of those nonlinear interaction terms, you still get the same type of oscillatory behavior. Now the way that the amplitude, the waves grow and decay looks slightly different, and actually might look more realistic in a sense, that the transition period is really fast. One wave forms, slowly decays a little bit, and so on. And I should also mention that there's other dynamics possible in this model besides just this oscillatory pattern that we show in these papers, like a hop bifurcation and things like that. Yeah, we hope there's a bifurcation. Yeah, but okay. And so all of this is part of an ongoing effort to better understand these interactions between convection and the mean wind through momentum transports. And I guess part of the big motivation here is that you'd hope with sufficient understanding you could faithfully parameterize momentum transports in GCMs. And I mean, it's not like that is a new idea. That's been there have been different strategies for doing that over many years, and there's still improvements being made. But as a final topic, I'd like to describe the way that we would like to approach parameterization of momentum transports, and that's with stochastic parameterization. And so just first a quick motivation of why you'd want to do a stochastic parameterization of momentum transports. And so the motivation comes from some papers by Tung and Yanai. These are observational data of momentum transports. There are issues with trying to observe momentum transports from observational data, which I won't really talk about here. So just assuming that this is faithful data of momentum transports. This is the mean and standard deviation statistics. So this top plot is for the zonal component of the wind. The bottom plot is the meridional component. And we are looking at the momentum transports, and then this term gives a sign to say whether it's accelerating or decelerating. So the fact that this mean is always negative implies that there is damping of the wind in the mean. And the same is true for the meridional component of the wind. So this is seeing in observations this idea of that clouds have a damping effect on the winds. It's sort of a cumulus friction. But the other really neat thing about what's going on here is look at these standard deviation bars of the momentum transport at every level. They are gigantic. So with such huge standard deviations, you would expect that if you were going to try to parameterize these effects, you might want to use a stochastic model that has a lot of variability to capture what's going on. And the other thing you might start to wonder here is, all right, standard deviation has the same width, whether it's positive or negative, so you might wonder, is there any skewness here? But there's actually examples of both strong acceleration and strong deceleration. So this is an example of really strong damping. It's a non-squall convective system that they looked at. So this is U on the left, V on the right. The solid curve is the wind itself, and the dots are the acceleration due to momentum transport. So this is really strong damping of about 10 meter per second per day due to this non-squall convective system. Now, on the other hand, you can also have really intense accelerations due to these systems. So this is an example of a squall line from that paper. So now the wind and the acceleration of the same sign. So this is going to be accelerating these low-level winds here. Okay. So this is the motivation for trying to use stochastic models for parameterizing momentum transport, that we want to capture these intermittent intense bursts, and and hopefully give more realistic variability of tropical convection in that way. So just to illustrate how tropical convective variability is lacking in some GCMs, this is a plot like Boulem had showed of observational spectral power with a background spectrum removed. And this is a typical example from 2006 of that type of statistic in the GCM. So the main point is that GCMs tend to have not quite the right variability for tropical convection, and it'd be an important step to try to increase that variability and make it look more like this. Okay. And there's been lots of work on stochastic models for tropical convection. We just saw a whole talk on them. So there was some work in 2002 by Boulem and Andy on some earlier versions of stochastic parameterizations. This work that I'm going to talk about now is from 2008, and it's on focusing on stochastic models for convective momentum transport. Okay. So the way we're going to parameterize convective momentum transport in a simple stochastic way is to have three convective regimes. So in Boulem's talk a minute ago, they had different cloud types that the atmosphere could be in. Now we're going to assume that a grid box could have a different convective regime. So it could be a dry regime with no clouds, so then there should be no effect of cumulus friction or convective momentum transport at all. There should be a regime with upright convection or with a case that's not organized like a squall line, and you would expect damping in these cases. And these would be cases where there's not much shear in the lower troposphere. And then we're going to have a third regime, which is basically a squall line regime. So this would happen when there's a moist atmosphere and low-level shear, so the squall line could form. And you would expect intense momentum transport, which could be upscale or downscale. Okay, so then the next question is, how do you decide which regime to be in? So as we saw in Boulem's talk, we have different variables that describe the different regimes, and we need to prescribe transition rates for how do we jump from one regime to another. And just to connect with some of the earlier stuff in this talk, you can think of this as a stochastic time delay in how the convection responds to the large-scale variables, because these transition rates will depend on the large-scale state. And so this transition rate is a stochastic time delay for how the convection responds. So these are the transition rates we chose for transitioning between different regimes. I won't describe any one of them in detail, besides just to mention that they depend on what the shear is doing, what is the mid-level shear versus low-level shear doing. They depend on the moist background state given by, say, your GCM is providing this information. These are just plausible based on observational work and cloud resolving model work. So I'll describe on the slide after this. I'll show one way that gets input in the model. And I guess this is, I think, the last piece of the model. So if you know what regime you're in, then you have to say, how does that regime feed back to the large scale? What are the momentum transports for each regime? So as a simple way to do it for a first try, we're just going to say it's in the clear skies case, there's going to be a weak damping. In the upright convection case, there will be a stronger damping. And then we need to prescribe the momentum transport due to the squall line. And so we're going to assume that has this type of form affecting the first and third baroclinic modes. I won't go into the details of where this comes from, but it's the same thing that I was showing in some of the earlier slides. Yeah. Do I need to define W prime? Well, in the multi-cloud model, W prime comes from the horizontal divergence. Well, in the baroclinic mode.
It comes from the shallow water approximations with the divergence. So there's two contributions. There's the first and second baroclinic mode divergence. And you just compute the W prime and U prime.
At lower levels and upper levels, both, yeah. Yeah.
How do you account for these transitions from geographical location to another geography? It depends on the geography also.
I'm sorry, if I understood right, you're asking, should the transition rates depend on geography too?
Yes. How do you account for the variation according to the geography?
That would, I guess, be provided by, that would be through the moist background state, which affects the transition rates, or the background shear profile at different geographical locations. Yep, provided by the larger scale model, the GCM model. Does that answer?
So this has to be trained for different locations, like will have a different pattern.
It should change depending on whatever the GCM says it is at that location at that time. That gets plugged in right here. This is say the water vapor at this GCM grid box at this time. So these are time evolving and spatially varying. And so the two are going to be interacting with each other. So just to describe one way that, there's quite a few things to choose here. So describe one thing to choose here would be how strong should this momentum transport due to the squall line be? So I'll describe our choice for that. It's going to depend on the moisture and the middle level wind shear. And so we chose this type of formula based on some of the cloud resolving model results of Liu and Moncrief. So they did 2D cloud resolving model simulations using these different wind shears. And for all the ones with the low level shear, you get a squall line. They all propagate in the same direction, but depending on what the mid-level shear is doing, you get different momentum fluxes. So we're going to build that into our squall line momentum flux by having the mid-level shear right here. Just one example for how we choose some of the things that it's going on. So we base it on lots of different cloud resolving model simulations that have been done over the years, or observational stuff too. Okay, and then as our simple GCM test model, we're going to use the multi-cloud model as a simple place to test out how this works. And so it's going to be this version of the multi-cloud model. There's no nonlinear stuff going on here. On the left-hand side, at least, there's plenty of nonlinear stuff here. And then we now use these momentum transport terms here on the right-hand side. Okay. And so we're going to have just a 6,000 kilometer periodic domain. We're going to use a 50 kilometer grid spacing to be sort of like a GCM. And so for this simple case, you just get one convectively coupled wave that's propagating around your domain. This is the deep convective heating of that convectively coupled wave. And this is showing the convective regime. So if it's white, there's clear skies. If it's gray, that's the upright convective regime. And the black is the squall line regime. And then this is this third baroclinic mode. And so just to show the structure of this wave, it has the typical tilted updraft structure of a wig wave. And so, I guess you can see you get some increase in variability from this, but not a ton in this particular simple case. One interesting thing that does happen is that the stochastic momentum transport generates a non-trivial mean flow. So comparing the zonal wind with stochastic CMT and without, and taking the difference, you get a non-trivial mean flow that develops due to having the stochastic momentum transport in there instead. It's kind of interesting. Okay. So to summarize everything, we were doing some multiscale modeling to understand and illustrate convective momentum transport, and there were kind of four main points in this talk. One is that energy transfers can sometimes be upscale, sometimes downscale. We showed some simple illustrations of this. Another thing is that if you have a multiscale wave or convection, you have to consider competition between the different components of the multiscale wave, the envelope or the fluctuations. Another important point is that there are time delays involved in in the interaction between a large-scale state and the convection. And then lastly, we showed a simple way of creating a stochastic convective momentum transport parameterization, which should be able to capture the intermittent aspects of CMT. All right, that's it. Thanks.
Do you include heat source in the form of W prime, theta prime, or in the full model, multi-cloud model plus CMT?
The heat source in terms of what?
In the form of W prime, theta prime,
the heat flux.
in the sense convective heat transfer term.
That is not explicitly put in, although I guess that would possibly be entering through
the heat equation is not, it's a linear equation.
Oh,
right?
sorry, the first model, yes. The very yeah, so the multiscale model in the first part of the talk, yes, there was W prime theta prime in there. It didn't seem to do much in this case because it's not a very large domain. 6,000 kilometer was the size of the domain, so you can't have a convergence if you only have one coarse grid box. If that makes sense.
Yeah.
Yeah.
I had a question about these intermittent aspects of momentum transport. Do you have any quantitative measure of how bursty that is? Because I have a lot of data from atmospheric boundary layers about what happens under neutral conditions, under connective conditions.
Yeah, that would be a good thing to look at.
Measures of burstiness.
So they plot, in Tung and Yanai's paper, they plot the PDFs at different levels. But yeah, I guess there's, like kurtosis. And
These are tropical boundary layers. There is wind shear, certainly.
Did you took the core, for example? I didn't took the core experiment?
No. It was made here, sir. Made here in India. In Jodhpur, for example. Jodhpur. In the north.
Yeah.
And even in nearly neutral atmospheric boundary layers, you know the Gini index, it's a kind of concentration index. Well, it is 70-80%. 1 would be completely burst. 0 would be very evenly distributed in time. So if you did that on a scale, the neutral boundary layer is already 70% burst. And you look at the traces of the momentum transport. It's not very unusual to find that the highest peak stress, let's say in a 10-minute, 15-minute record, can be anywhere from 10 to 50 times the mean.
Yeah.
And if you have unstable convective conditions, it's even more.
Oh, I bet, yeah.
Slide where you showed the email 2006 you mentioned. And you mentioned that all the GCM doesn't capture the MJOs and so on, but I feel that is valid for GCM with conventional parameterizations, right? I mean, even if we use some of the super parameterization multiscale modeling framework, some of the wave power spectrum has definitely improved.
That's right. Yeah,
you agree with that?
A super parameterized GCM can do much better than this. And in fact, some GCMs...
This is valid for those GCMs which use the conventional parameterization.
Yes, that's right. Yeah.
Okay, the second,
Sometimes they have waves, but they propagate too fast.
Right. They looked at 14 different cases here, and it's all over the map for what it looks like. Some of them look like this. Some of them have a Kelvin wave, lots of Kelvin wave power, but at the wrong phase speed. It's all over the map.
But I want to comment on your comment. CAM superparameterization makes all these improvements, but it's still too expensive to run in operational ensemble mode. You can't run it.
It doesn't have CMT either.
And it doesn't have. Okay, Mitch.
Yes. The most superparameterization models don't represent CMT.
Right.
Yeah.
That's because they chose
You're right. You're absolutely right. Yeah.
One more. You showed that in the if there is a westward tilt, then there is a resultant CMT transport and westerly burst eastward. So can you speculate if there is in case of northward propagation, boreal summer, if there is a southward tilt,
I don't
Will
know
there be
how they.
analogous, I mean,
I don't know
towards
how
the
they
northward
tilt in the
propagation?
north-south direction.
No, in the
Biello and I, in our old MJO work that Sam referred to, looked at north and south tilts too.
Oh,
Yes.
I see. That's
There are north and
meridional
south tilts, meridional tilts that play a role. But before you jump to thinking about monsoon, as you're probably thinking, this is at the equatorial beta plane model, not in an F plane model.
Yeah.
Okay.